Professor, quando você quiser começar aqui na Unicamp já tudo ok.
Ok, então eu vou começar. Okay, good afternoon, everybody. I'm going to start now. It's on time, 2 o'clock. Today it's going to be the first of 3 classes about Exergy. Okay, we're going to talk today about the fundamentals of this area, exergetic analysis. And then we're going to have 2 more classes, one related to the separation process, which is the last one actually, and the second class on exergy, I'm going to talk about chemical exergy, okay? So this is a very, very important subject, and if you have any doubts because the subject is very, very extensive, please interrupt me and ask questions, okay? There's no problem. We have a lot of space to deal with this subject. So as I was saying today, I'm going to talk about exergetic analysis and the second title, integrating the first and second laws of thermodynamics. What I like about exergy, what I most like about exergy is that it's a thermodynamic property that combines both aspects of the first law, that is of energy conservation, and also of the second law, which is more related to the quality of the transformation processes, okay? Well, let me just introduce this subject. I'm going to recall this energy flow. That's the Sankey graph from United States Energy Use in the year of 2013. I'm going to use a lot this graph, and what I like it's that, well, you can see very easily the primary sources being transformed into energy vectors or energy carriers, and these energy carriers are being applied in different sectors, residential, commercial, industrial, and transportation. We saw in, I don't remember, the first class about thermal conversion, the second law of thermodynamics. Just to remind you, what is it? Actually, if you have a thermal source, which can be, for instance, burning coal in a thermoelectric power plant, it will produce a certain amount of heat. This heat will flow to the environment because there's a difference in temperature here, and from this flow we can somehow, or through a thermodynamic cycle, we can extract organized energy, which we can transform into electricity and sell on the grid. We saw that the second law, the first law states that, well, energy balances. So I'm going to write it down here. The first law says that Q fuel equals W surplus, okay, plus the heat rejected. Okay, that's the first law. The second law actually tells us something about the efficiency of this conversion, because our intention would be to convert 100% of the heat supplied to work, to electricity. And we know that this is not possible for a finite temperature difference between the thermal source and the environment. Okay, so that's the second law, and that's the first law. When you look at the consequences of the second law on this type of graph, what is very, I would say, surprising is the amount of rejected energy. When you look at the right side of this Sankey diagram, you see that, well, 38% of the total input becomes what we call useful energy. That is energy that has been effectively used to transform, to transport, or something like that. And the most part actually is rejected, 59%. Why is that? And can we do something about it? Is it possible not to reject energy? Well, we know that it's not possible not to reject some amount of energy, but is this too much, or is this close to the maximum efficiency that we can infer from the second law of thermodynamics. You see, all these rejected energy actually, most part, comes from this application, electricity generation, and I already mentioned that here, except for, let's say, solar photovoltaic energy and possibly to wind energy, the remaining is all based on thermal cycles. So it's a Rankine cycle, a Brayton cycle, okay, and it's exactly something like this, and you know that there are some amount of heat that's going to be rejected to the environment. The same applies to the transportation sector. Those are internal combustion engines, for instance, or jet turbines, as we say, no? And they are Otto cycle or diesel cycle or even the Brayton cycle. So it's the same as the Rankine and Brayton. These cycles are thermal cycles, and they do reject some amount of heat. Okay. So the question is, how to maximize the conversion efficiency of an energy vector to useful energy? Useful, or by useful I mean electricity, kinetic energy, and so on. Okay, how can we maximize? Okay, that's the question that we're going to deal today. Actually today, since it is the introduction of the concept related to Exergy, I'm going to be asking a lot of questions, so I want you to answer in your minds, okay? Because actually we're not in the same place, in the same city, so it's going to be a little awkward if you try to, at the same time, answer my questions. So they are rhetorical questions. Okay, so let me start with the first question. Remember, I'm going back one slide. We want to maximize the efficiency of the use of some vector like this, some energy carrier. The efficiency of coal, the efficiency of gasoline, ethanol, and so on. Okay, so if the problem is to generate energy, useful energy, from which of these two systems is it possible to generate the greatest amount of mechanical work? Okay, so you have two choices. You can ask for a bottle of compressed air. So this is air, not argonium. Okay, this is still in Portuguese. At 10 bar, 25 degrees, or a bottle full of air at 1 bar, 25 degrees. From which one of these two bottles do you think it's possible to generate the greatest amount of energy? Mechanical energy, okay, or organized energy? I'm sure. Yeah?
I think 10 bars.
10 bars, okay. Okay, so probably you are thinking in, for instance, using a nozzle. So you convert this pressure into velocity, okay, so through the nozzle, you accelerate the gas flow, and this gas flow will, for instance, drive a turbine. And from the turbine, you can generate electricity. Okay? So that's the most, everybody thinks about that. But what if the environment, the pressure, the environmental pressure is 10 bar? Okay? You see, so the pressure inside the bottle is 10 bar, but outside the bottle is also 10 bar. What's going to happen? Actually, there's not going to be any flow because the pressure is the same, so you cannot generate electricity. Okay? So let me continue with these questions, because actually what I want to do is to motivate the conclusion, which we're going to arrive in a few slides, okay? Okay, so now our environment is at 25 degrees, and our environment, I'm saying, okay, is at 10 bar. So the same question applies. From which of these two systems is it possible to generate the greatest amount of mechanical work? Air at 10 bar, 25 degrees, or methane at 10 bar, 25 degrees? from which of these two systems do you think is it possible to generate the greatest amount of mechanical work, electricity? Okay. Well, probably you would say, at least when I first saw this subject, I was always making these choices that I'm showing you, okay? So probably we would choose methane. Why is that? Well, maybe you guys are thinking what I thought at the time. You're going to get some oxygen, you're going to burn methane with oxygen. So here you're going to have high temperature, which will expand through the nozzle, and the same way you can produce velocity, macroscopic velocity. Okay, this velocity will dry this turbine. Okay, well, but the same problem may apply. Okay, what if the environment, the chemical composition of the environment is methane, also at 10 bar, 25 degrees. Okay, so the same conclusion. You cannot generate energy, organized energy, if the environment is the same as your thermodynamic source. Okay, so the conclusion. That's why I made these questions, because for you to be sensitive to this conclusion. The capacity to generate work is a combined property of the thermodynamic state of the system, defined, for instance, in terms of its canonical properties, pressure and temperature, for instance, and the environment. Okay, so you cannot separate the thermodynamic system, the substance containing energy. Okay, you cannot separate that from the environment. The amount of energy that you generate depends on both the thermodynamic state and also of the environment. And that's one big problem, because until now we do not have any direct means of accounting for the environment into our analysis. Okay, so that's the main role and the main advantage of using exegetic or exergy in exegetic analysis. Okay, so let me move further. So our problem is to generate the maximum amount of work, mechanical energy, okay, from a system which is in a specific thermodynamic state, a certain level of pressure, a certain temperature, and the volume. Okay, so we're going to generate energy by bringing this system to equilibrium with the environment. Okay, so what we're going to do actually is this. We have, let's say, gas at very high pressure here, let's say 10 bar, for instance. Okay, and suppose the temperature here is 200 degrees. Okay, the environment is at 1 bar, and let's say the temperature here is 25 degrees. Okay, so this difference between the thermodynamic state of the system and the conditions of the environment, this difference is what's going to drive our energy generation. Okay, so we want the maximum amount of energy, and we can we can allow the system to equilibrate with the environment. So this can be done by infinite pathways. Okay, we can make a very complicated trajectory like this, Okay, we can allow this equilibrium. By equilibrium, I mean the temperature from 200, it's going to go down to 25. The pressure of the thermodynamic system is going to decrease from 10 to 1. And I'm saying that this difference, or this transformation, there are an infinite number of possible transformation. Okay. What we can infer from the second law of thermodynamics is that the maximum amount of work actually is obtained when you choose a reversible transformation. Okay? And so that's it. You get the maximum amount of work when you allow the system to go to equilibrium through a reversible transformation. Okay? And the system, the equilibrium with the environment, well, whatever this environment can be. It can be, for instance, as I said, as here today, possibly air at 1 bar 25 degrees, or as I mentioned, air at 10 bar 25 degrees, or methane, or vacuum, and so on. Okay, so that's the whole point. Okay, we're going to elaborate on that. So some definitions, which were first elaborated by Gibbs. Gibbs, as in Gibbs free energy. I don't know if you guys are from the chemical field. In chemistry, we use a lot of Gibbs free energy. Okay, so his idea was that he called useful work potential. Actually, this is a name for something very special, and we have a lot of different names. I'm gonna highlight that in a moment. Okay, so the maximum or useful work potential is the maximum amount of mechanical energy that one can obtain from a system, the difference being inevitably lost to the environment due to implications of the second law. This is actually exergy. As I was saying, there's a lot of names for this useful potential work, such as available energy, exergetic energy, availability, reversible work, and so on. Depending on the authors, there's no general agreement on these names. Okay, I like this one, exergy, and I adopt this one because, well, you know, exergy actually is energy. Okay, exergy is energy, but not all types of energy are exergy. Okay, so if you are not used with these terms, exergy, think about electricity. You can replace in your mind the term exergy by electricity. Okay, so the question is simple: what's the exergy content of 1 kilogram of gasoline? Okay. So you could answer this question like this. The exergy content of 1 kilogram of gasoline is the maximum amount of electricity that I could generate with this kilogram of gasoline. Okay? So that's the idea. We're going to work in order to obtain the mathematical definition of exergy. Okay, and the interpretation is just as I said, the maximum amount of mechanical energy. Okay, so in order to find this mathematical definition of exergy, this special kind of exergy, we're trying to build a kind of an exergy meter. How can we measure? How can we gauge the amount of energy, the amount of exergy, for instance, contained in a flow of heat, as I'm showing here. So we have a heat source, we have a heat absorber, okay, and let's say I have 10 megawatts of heat flowing from the high temperature reservoir to the lower temperature reservoir, okay, 10 megawatts of heat, and how much of these 10 megawatts correspond to exergy or electricity? 8 megawatts, 6 megawatts, okay. So we can measure this amount by saying that it is equal, thinking about the definition that I just showed you, this amount of exergy actually is equal to the work produced by a reversible cycle operating between the thermal reservoir and the environment. Okay, so our exergy meter actually corresponds to using this heat obtained from the heat source to drive a reversible cycle, reversible cycle, a Carnot cycle or a Stirling cycle, for instance. Okay, So that's what we're going to do. We have our heat source, okay? We use the same amount of heat, Q, okay, to drive a Carnot cycle. And the Carnot cycle is operating between the heat sources and the environment down here, okay? So this work obtained here is actually, by definition, equal to the exergy content of this heat flow, okay? And we know that due to the implications of the second law of thermodynamics, xq is smaller than qq, okay? We know that because this difference here, Tq minus T0, which is the environmental temperature, is less than infinity, okay? It's a finite temperature difference. Okay, so that's let's say the electronic circuit of our Exergy meter, okay? And how about, so if I want to calculate the amount of Exergy, I do this calculation. But we can also figure, if I have a thermal machine as in here, I know how to measure the heat content of the heat supplied to the thermal machine, okay, by making this measurement here. But how about measuring the amount of exergy from contained in this rejected heat to the environment? That's the same approach. We imagine a thermal machine between this reservoir and the environment being supplied. We supply the same amount of heat. Okay, so we imagine a reversible machine here between this lower temperature reservoir, lower when compared to the heat source. Okay, so in this situation, it's going to play the role of the heat source, and the same amount of heat, QF, see QF here, is driving a Carnot cycle. Okay, so this amount of work here is, by definition, the exergy content of this heat flow here. Okay. Okay, so I can go on, and if we try to make a Sankey diagram, as I showed you before, regarding the energy used in the United States, we see that xq, the amount of heat contained in this heat flow, is greater than xf. So we have a step here, we have a gap here. Okay, why is that? Well, we know this because if we do the calculations, okay, let me just show you the formula. If we do the calculation, okay, xq is qq multiplied by the efficiency of the Carnot cycle, okay, which is calculated like this. T0 is the environment temperature, and Tq is the temperature of the heat source, okay, and the same for xf, only that the heat source is this blue thermal reservoir, Tf. So we know that Tq is greater than Tf, okay? Tq, I'm going to write it here, Tq is greater than Tf, okay? So this means that this efficiency is greater, 1 minus T0 over Tq is greater, it's a greater number than this one, okay? So we know that xq is greater than xf as it is drawn here, okay? So actually there's, as I'm pointing out here, there's exergy destruction, okay? There's exergy destruction, and it occurs due to the presence of irreversibilities, okay? So actually, we're going to come back to this. There is exergy destruction where there is entropy generation. And entropy generation occurs when there are irreversibilities. By irreversibilities, you can list, for instance, friction, chemical reaction, a shock wave in a supersonic or transonic flow. Okay, so all these phenomena generate entropy, which causes exergy destruction. Okay, so that's the point. We now know that exergy can only be destroyed. Okay, you cannot increase exergy. Okay, and we know how to measure exergy. Okay, measure exergy. It just at least we know how to measure exergy in heat flow, the exergy content of heat. Okay, so let's move on. We're going to apply these ideas because till now they are only ideas and concepts. Okay, we're going to apply this in a closed system, and then we're going to apply this in an open system in order to obtain workable formulas with which we can analyze our problems, which we're going to do during the next 2 weeks. Okay, next week I'm going to talk about chemical exergy, and the following week I'm going to talk about I'm going to make an exergetic analysis of a separation process. Okay, and see how this applies to, for instance, to harvesting biomass in the fields, for instance. Okay, so let's start by applying these ideas to a closed system. Okay, so we have a system which is actually, a system is a certain amount of mass confined by a virtual surface, and if it is a closed system, there is no mass flow through this surface. Okay, so this confining surface may be the cylinder and the piston. Okay, and the system actually is this I don't know, this orange substance or yellow substance here. Okay, this system is at a high energy state, at a high level, high pressure P, and a high temperature T. The environment is at T0, and the pressure of the environment is P0. Okay, so if we allow this system to expand in order to equilibrate the pressures, so P, the internal pressure of the system, is going to become equal to P0, and also if we allow heat to be exchanged, T is going to become equal to T0. Okay, so two things are going to happen here. We're going to have production of work, positive or negative, we don't know yet, depends on P and T, and also heat flow, Q. Okay, and that's what we're going to do, and we're going to analyze this work obtained here, produced by this force here, and the exergy associated with this heat flow down here. Okay, so we want to produce useful work. That's another name for exergy. And let's say that we're trying to raise a person like Homer Simpson. Okay, so in order to increase his potential energy, we need to apply a force. Okay, and we need that this force produces movement. Okay, so this useful work is a force times a displacement. Let's say D for displacement. Okay, so let's make some considerations here. The amount of useful work going out of the system, the amount of work produced by the system, just an observation before I go on. The system, I'm going to use this space here, the system, the yellow substance is going to produce a certain amount of work, and part of this work is useful. with useful, okay, which is used in order to increase Homer-Simpson height, okay. But part of this work is, let's say, lost because, well, I'm not elaborating on that. We're trying to compress the atmosphere here, okay. But part is not useful. So I'm going to calculate all these components and try to infer the definition of exergy from this analysis. Okay, so the amount of work produced by the system's expansion is this amount here. Okay, a force, the force down here. Okay, which is P times the area of the piston. Okay, times, let's say, the displacement here, a small displacement d, times d. So force times displacement. What happens is that A times d equals V, the volume, actually delta V, okay? Delta V, okay? So in differential terms, we can write this. Del W is equal to P dV. Okay, so let's move on. And so this is okay. This is the work produced by the system. Okay, and now I'm simply adding plus or less P0 dV. Okay, in this formula here, and we obtain the formula down here. Okay, so by doing this, I can make some rearrangements here. I can write P minus P0 dV. Okay, so the minus here already used, and it remains P0 dV. Okay, so let me ask you, what is P minus P0 dV? Okay, P minus P0, if I multiply by this by A, this is actually the force applied to Homer-Simpson, okay? Because actually is the resulting force from P, which is acting from downwards upwards, which is acting upwards, and P0, which is opposite, okay? So this is the resulting force, okay? And if I multiply this by D, okay, if I multiply this by the displacement, F, this force here applied on Homer-Simpson times D is useful work, okay? But on the right, the left-hand side of this equation, A times D is delta V, okay? Okay, so we can infer from this that this component here is useful work, and this is what I was referring to as not useful work. We're going to see it in detail in a little while, okay? Okay, no problem. So if I want to calculate the finite quantities, I integrate this, so I obtain, that's the mechanical work released by the system when I let it go to equilibrium with the environment. So this is the amount of work produced. This is what's really useful, and this is what's not useful. Okay, but you know, in this integral, P0 is constant because it's the pressure of the environment. So if we integrate here, we obtain simply P0 times V2 minus V1 because it's constant. Okay? Okay, let me give a name to this. Okay, so the first component is, well, useful work, and the other component here is work absorbed by the environment. Why is that? Well, actually, if the system the orange substance is expanding, it's consuming some volume which is taken from the environment, okay? So when it expands, it tries to compress the atmosphere, okay? And this, makes a difference, because expanding in the vacuum is different from expanding in the atmosphere, for instance. So in the vacuum, P0 equals 0, and we don't have this, okay? So that's another important conclusion. The amount of useful work that you can get always depend on the thermodynamic state and also on the environment. Depend on both. That's a combined property, okay? So let's continue, because what I want to obtain here is a working definition of exergy. Okay, I want to obtain a mathematical formula which is convenient for the definition of exergy. Okay, so and just rewrite the expression that we obtained. So work produced by the system is equal to useful work plus work against the environment. Okay. Another definition that I want you to remember is the definition of entropy. Okay. So entropy is defined as delta S, the variation in entropy, equals to integral of del Q over T. Okay. That's the definition of entropy, and this integral is calculated on a reversible trajectory. Okay, that's the definition of entropy. Entropy, and I already mentioned, is a measure of the level of disorder of the system. Okay, you have actually 4 types of entropy, and they are equivalent. You have what we call thermodynamic entropy, which is this one. You also have what we call Kolmogorov entropy. Has a different definition, but is completely equivalent. Okay, and you also have information entropy. Okay, which is, well, actually it's applied in information theory, but they are all the same. A measure of the level of disorganization of a system. Okay, so just a quick reminder of the definition of entropy. Okay, so now with these two, a conclusion and a definition, we're going to analyze the exergy content of this heat flow, because we know how to calculate the exergy associated with this force, which is used to raise Homer Simpson. Okay, so when I do the calculation, if I want to measure the amount of exergy contained in this heat flow, I imagine a Carnot cycle between the system and the environment, as it's shown here. Okay, and the exergy content of this heat flow is the amount of work that I obtained from this reversible machine. And this calculates as it's shown here. Okay, I multiply the amount of heat exchanged by the efficiency of the Carnot cycle. Okay, this is 1 minus Tf over Tq. Okay, actually this is valid for all reversible cycles. Okay, so that's it. It's no problem. So combining all these formulas, okay, I can write this down. Okay, this is first law of thermodynamics. Okay, del Q here equals to del W. MT stands for thermal machine. Okay, plus the heat rejected to the environment, which is down here. Okay, and this is equal to T0 ds. We are using this definition here. Okay, so when I apply the first law to the system, okay, this is the first law applied to the orange substance, we obtain that the variation of its internal energy equals to the energy that is being removed from the system, which is some amount of energy in form of work and some amount of energy as heat. Okay, so that's the first law applied to, this is the first law applied to this thermal machine here, okay? And this is the first law applied to the orange substance here, okay? So combining again, okay, that's a little tricky, but well, it's very simple actually. So combining these two formulas, we obtain that du equals minus del W plus T0 ds minus dW useful plus P0 dV, okay? That's a mathematical manipulation. I just translated the formula here. And continuing and thinking about our old definition, okay? The total useful work equals to the useful work obtained from the heat flow plus the useful work associated with this force here, which raises Homer Simpson, okay? So we get that this is minus du minus P0 dV minus T0 ds, okay? And if we integrate this, we obtain this formula here, okay? Finally, this is what we were looking for, okay? And this is the total useful work calculated in terms of thermodynamic properties of the system at pressure P, temperature T, okay? U, it's internal energy, V, its volume, and S is its entropy at pressure P, temperature T, okay? And also, we have the effect of the environment in this definition. We have U0, V0, and S0, which are, respectively, the internal energy, the volume, and the entropy when the system is in equilibrium with the environment, okay? When its pressure becomes P0 and when its temperature becomes T0, okay? So this formula can be used to define exergy, okay? So we're going to define exergy as exactly this formula that we just obtained, okay? This is the definition of exergy. An observation, sometimes I use the letter X to refer to exergy, but, so it's exergy, okay, exergy, but sometimes it's quality. Quality in Portuguese is título, okay? That's the mass of vapor divided by the mass, the total mass, the mass of the mixture, vapor plus liquid, okay? In order to avoid confusion, when both terms appear, sometimes I'm going to use the letter E to refer to exergy, okay? When both concepts appear in our analysis, okay? Just an observation. It's self-evident, no problem, but just to remind you this, okay? So, let's analyze this definition. As I was saying, U0, P0, V0, and S0 accounts for the influence of the environment, okay? Accounts the influence of the environment. Very, very, very important observation. U0, P0, V0, and S0 are not thermodynamic properties of the environment, okay? They are thermodynamic properties of the, let's say, orange substance when it's in equilibrium with the environment, okay? So if our orange substance is nitrogen, that's the internal energy of nitrogen at 1 bar 25 degrees, for instance, if our environment is at this pressure and temperature. Okay, V0 is the volume of nitrogen at 1 bar 25 degrees, and S0 is the entropy of nitrogen at 1 bar 25 degrees. Okay, so because sometimes I see students make confusion with this concept. Okay, so they account for the influence of the environment, and well, everything, all these terms we call thermodynamic exergy, but as I was saying, this can be referred to as available energy, exergetic energy, availability, reversible work, and so on. Different authors use different definitions. As I was saying, I prefer this definition because exergy actually is energy. Its physical unit is watts, for instance, or joule. Okay, and if you use this availability, for instance, you may not think it's energy. It's an amount of energy. Okay, well, if our system has other types of useful work, other energy components from which we can obtain useful work, no problem, we simply add these components here. So if our system's center of mass has a potential energy or kinetic energy, I simply add here, okay, in the definition of exergy, okay, and if there's a difference in terms of chemical composition, I can add another term here and call it chemical exergy. We're going to see chemical exergy in our next class next week. Okay, we're going to see this next week. We're going to focus today on this component here. Okay, so that's the definition. So sometimes we're going to consider this other components here. Sometimes we're going to disregard them because let's say that the kinetic energy of our system is not changing. Okay, or its chemical composition, or I was saying that our system is, or orange substance is nitrogen. It expands and its temperature equals the temperature of the environment, but it's still nitrogen, 100% nitrogen. It's not changing its chemical composition. Okay, so when we have, just to elaborate a little bit on this, we're going to see it in a full content next week. Let's consider one of the questions. Okay, so we had methane at 10 bar 25 degrees, and the environment is air, not argonium. Okay, air at 10 bar 25 degrees. So I can burn this methane with oxygen present in the air. It also has nitrogen. Okay, I still get a lot of heat from this, and this heat can be used to accelerate the flow. Okay, and this flow is going to drive this turbine here. Okay, so let's analyze all transformations. Okay, because you see, my point here is that because the pressure is the same as the environment, 10 bar, 10 bar, the temperature is the same, 25, 25. When I open this valve, if I don't do nothing, there's not going to be a flow, okay, because the pressure is the same. But if I allow it chemically to react chemically with oxygen, I get heat, and from heat I can obtain work. Okay, so the concept of chemical exergy is the same. The maximum amount of work when its constituents are chemically transformed to those constituents of the environment. Okay, so at the beginning here we have, well, the exergy of methane here is defined as the same. Okay, a thermodynamic component plus potential plus kinetic energy, or exergy, and chemical. So in the first stage, or inside the bottle here, all this is zero because U U is equal to U0. Why is that? Because the pressure is the same and the temperature is the same. Okay? And remember, U0 is the internal energy of methane at 10 bar 25 degrees. Okay? Which is the same of the environment. So this is 0. Likewise, V minus V0 and S minus S0 is 0. Also, well, we're disregarding potential and kinetic energy, so the exergy content of this bottle is entirely due to its chemical exergy, which we do not know how to calculate until now. Next week, we're going to see how we can calculate the chemical exergy of a substance. Okay? So, inside the bottle, 100% of the exergy content is due to chemical exergy. What happens when we have this transformation here, when this combustion, this chemical reaction? So what happens is that we get heat, so exergy from, let's say, the chemical component is transferred to thermodynamic exergy, is transformed to thermodynamic exergy. Why is that? Because, well, temperature is going to be different here inside the combustion chamber. Pressure is going to be different, so the volume is going to be different, internal energy and entropy. So these components here are different than 0 now, okay? So chemical exergy was transformed to thermodynamic exergy. And what happens now when this high pressure, high temperature gas flows through this nozzle, accelerates through this nozzle? All this thermodynamic exergy actually is now transformed to kinetic energy. Okay? Why is that? Well, the chemical composition now is the same of the air. You know, air contains CO2, H2, and N2. And so the temperature is the same, pressure is the same of the environment, again, 10 bar 25 degrees, so, but it accelerates. So the thermodynamic component becomes kinetic exergy or kinetic energy. Okay? And we can draw a conclusion from this. Okay? The potential to generate work, and by work I mean organized energy, exists when there are differences between the system and the environment. Those differences may be in terms of thermodynamic properties, chemical composition, kinetic energy, potential energy, and so on. So the key word here is differences. You generate organized energy from differences. Okay? Keep this idea in mind. We're going to come back to this in a few moments. Let me just give you another example related to chemical exergy, which is as we call the osmotic elevator. Okay, you can produce useful work. We're going to use it to rise Homer Simpson, to change his potential energy. Okay, just exploiting a difference in terms of concentration. Okay, suppose that this dark orange here is our environment, which is at a high concentration, water and salt, for instance, and we have a system, okay, which is at a low concentration. So sweet water and seawater here, let's say. Okay, so if we allow water, because if we put this in contact through a permeable membrane, what's going to happen? You know, pure water is going to flow through this membrane in order to equilibrate the concentration here. Okay, so when this happens, what's going to happen? Well, you're going to have a force pushing Homer Simpson upwards. Okay, and well, this will go until things equilibrate here. Okay, so this actually happens. Well, this is exactly what happens in a tree, for instance. Okay, I'm going to show you. And we could even use, if we have a infinite supply of low concentration fluid, we could use this to produce exergy. So there's pure water always flowing here in order to cancel out this concentration difference. Okay, and if we allow this water to flow using its potential energy, and if we replace the high concentration water here, we can generate electricity, exergy, from this difference in concentration. Okay, and this is exactly what a tree does. A tree, you know, I don't know if you ever asked yourselves why the roots of the tree, what kind of force makes water enters the tree fibers and goes upwards here. What drives water from let's say a lower position to a higher position here? Okay, that's exactly what's happening here. There's a difference in terms of concentration, and just an observation, the pressure inside the tree may reach something like 200 bar, for instance. Okay, so it's a very high pressure. What pumps water from the soil here into the tree from a lower pressure to a higher pressure, such as 200 bar? What's this pumping force is the difference in terms of concentration. Okay, and actually, if you look at the bigger picture, what maintains this difference in concentration? Okay, so suppose this is the sea and this is a river. Okay, which contains no salt, supposedly. What actually maintains this difference? And you know, well, the picture here is not very accurate because, well, you know, the river is on the continent, so it's on higher grounds. And what makes water, what pumps water from the sea to the top of these mountains and hills? Actually, is the solar energy through evaporation. Okay, water is evaporated from the sea. Okay, and it precipitates on land. Okay, so this difference is actually solar energy, this difference in concentration. So if we build this kind of osmotic power plant, it's still solar energy. Okay, why? Because the fundamental driving force is still the same, except for nuclear reactions, which is not well, it's not a solar energy, but it was due to a supernova explosion. Except for this kind of let's say second order solar energies, all energies are coming from the sun. Wind energy comes from the sun. Petroleum and coal and gas, natural gas, also from the sun, because it was biomass, fossil biomass. Okay, and biomass, you know, is produced from solar energy. Okay, so let's make a consideration here. If exergy, remember I said that exergy can only be destroyed in this process. I'm showing you very complex processes, and I already mentioned that exergy can only be destroyed because entropy is always being generated. Okay, so if exergy can only be destroyed, this means that the total exergy of the universe is decreasing and that all differences tend to equalize. Pressures and temperatures become the same, differences in chemical composition disappear, and so on and so forth. So what this means, okay, you know, Homer Simpson is thinking that is considering the universe as a closed system. That's why why this consideration is here. Remember, we are analyzing a closed system, So if we consider the universe as a closed system, well, Exergy can only be destroyed, and this means that, well, in the near future, not near future, in the far future, we're not going to have differences in terms of pressure, temperature, chemical composition, and so on. And remember, I'm going back some slides. It's worthwhile. We obtain useful energy from differences. And now we are concluding that in the future, there's not going to be difference. So what's going to happen in the far future? Okay, so let's think of the universe as a closed system. So this is our closed system here. Okay, it was created in the Big Bang. This is time, this is space. Okay, so what's happening right now? We know the universe is expanding, okay, at increasing speeds, actually. That was Hubble's finding, okay? And as we know that all differences are decreasing, so the universe in the far future is going to end on what we call a big chill, okay? There's no difference in pressure, temperature, chemical composition, so there's no useful work. It's simply going to explode, expand, and then it's going to stop, and nothing's going to happen. Okay, so this is one possible end for the universe. You know, there are other possible ends. Okay, this is what I call the thermodynamic view of the universe's future. Depending on the amount of mass, especially dark matter and dark energy, if there's enough dark matter in the universe, sometime in the future it's going to start attracting and contracting the universe, and it's going possibly to end in what they call a big crunch. And possibly in this situation the universe is periodic. Okay, the universe may behave like this. For instance, let me make a drawing here. A big bang, big crunch. Big bang, big crunch. Big bang, big crunch. So a periodic universe. Okay, this is a possibility. But if there's not enough dark matter to slow down universe's expansion and start to contracting it to the big crunch, possibly the universe is going to expanding and accelerate, and the end is we're going to have a ripping of the time-space fabric. Okay, so that's what they call a big rip, and it depends on the amount of dark matter. Our view, the view of people studying thermodynamics, is the big chill, because, as I said, the entropy is always being generated, so Exergy is always being destructed. So all differences are decreasing. Okay, this is a possibility. But, well, we're not very much concerned about this right now, and especially in this course. Okay, so as I mentioned, we analyzed a closed system. We obtained a definition, a working definition for Exergy, and now I want to make the same analysis to an open system, okay? Because, well, it's more appropriate to the analysis, to the practical problems that we're going to see the following 2 weeks, okay? So, open systems. An open system, just remember the definition. A system is an amount of mass confined by a virtual mathematical surface, okay? And if it is open, there is flow of mass through the surface confining the system. Okay, so there's mass flow in and out, and this mass entering and exiting the system contain energy, so it contains Exergy. Okay, but also the system can export work and produce work surplus or surplus mechanical energy, and it can also transfer heat to the environment. Okay, so that's the analysis that we're going to apply. Okay, you remember when I showed you this, and also from your thermodynamic courses, we have. Let me go back one slide here, just to use a figure of speech. When I want to inject, let's say, inject mass in the system, something is trying to call. Let me say I'm not available. Okay, so when we try to inject some amount of mass into the system, the pressure may be different. So the system may be at 100 bar, and outside of the system we may have 1 bar. So I have to apply a certain amount of force in order to inject this amount of mass into the system. So that's why I use these two syringes, okay? And to inject the amount of mass inside the system, I have to apply a force F times the displacement, which will correspond to this volume in red here, and F times displacement equals work. Trabalho em português. Sorry, I forgot to translate this part of the slide. Okay, so this is what we call flow work. You know this, and just a reminder. Okay, and flow work, as I showed you, is this work here in order to introduce the red amount of mass inside the system. So it's force times displacement. Force is pressure times area, the area of the piston here, okay? And area times delta x is equal to V, or delta V, okay? So flow work is always PV, or P delta V, okay? And the same applies to the mass that is going out of the volume, okay? So we have this formula for the flow work, PV, okay? Now I'm doing the same thing, okay? I'm trying to calculate the Exergy content associated with this flow work. So we have flow work, and we have, I'm going back 2 slides, when I inject, this P0 is the force applied by my finger, okay? And you also have the environment pressure outside here, helping push the fluid inside the volume, okay? So I'm subtracting, okay, P0 minus V in order to account for the resulting force that is actually forcing the red fluid inside the volume, okay? So the flow Exergy is P minus P0V, okay? And we can conclude that the total Exergy, or the Exergy associated with this mass flow, is the closed system Exergy plus flow Exergy. Okay, when we write down the definition here, so that's the closed system definition of Exergy. We just use it in a few slides earlier. Okay, that's thermodynamic Exergy, and this is flow Exergy. You see, we can rearrange the terms here. I'm going to show you. So if I combine U plus PV, okay, and then U0 plus P0V, okay, it's here, I obtain this definition. Why? I don't know if you remember, that's the definition of enthalpy, because enthalpy is by definition internal energy plus PV. Okay, that's a definition of enthalpy. Okay, so I can write, I can modify the definition of Exergy in order to adapt it to open systems by simply using enthalpy. Okay, so it becomes actually easier. Okay, so let's move. And the same, if I have potential Exergy, kinetic Exergy, and chemical, I simply add these terms on the right hand side of the definition. I can have magnetic, exergy, all other types of energies, okay? And I can also work in terms of specific properties. Capital X equals small x divided by mass, okay? So that's the capital letters mean absolute quantities, and small letters mean specific quantities, specific in terms of mass or moles, okay, or moles. Sometimes it's more convenient in terms to work in terms of moles, molar basis, okay, just to have this definition. So another interesting aspect that we can see now is the definition of what we call second law efficiency, okay, which also have other names: rational efficiency, exergetic efficiency, and so on. Okay, I'm more used to this term, second law efficiency. So exergetic efficiency, as Gibbs called, is the ratio of the first law efficiency of a thermal cycle to the efficiency of a reversible cycle operating between the same temperatures. Okay, why is this convenient? Because, you know, when I say an internal combustion engine, the efficiency of a internal combustion engine is, let's say, 30%. This is a good or bad result? Well, depends, because if the efficiency of a Stirling engine, ST, at the same working between the same temperatures, if it's 31%, okay, so this thermal machine here is actually very good, okay, because it's almost the maximum possible efficiency, okay. But if instead of 31, a reversible engine between the same temperatures has 81% its efficiency, so 30 is less than 50%, less than half of the efficiency. So it's not a very good result. So what Gibbs defined as second law efficiency, I'm going to use this part here. So the second law efficiency is actually the actual efficiency, or the first law efficiency, divided by a reversible efficiency between the same temperatures. Okay, so you see 31% a reversible efficiency between the same temperatures. Okay, so you see 31% efficiency of a reversible machine between the same reservoirs. Okay, so in the case of machine A, this efficiency we can calculate 1 minus Tf, the temperature of the cold reservoir, divided by the temperature of the hot reservoir. Okay, so this is this becomes 0.03, which is 30%, divided by the efficiency of the reversible machine between 600 and 300 K. This is 60%. Okay, so that's the second law efficiency of machine A. Let's do the same for machine B. Okay, so the same calculation for machine B is 0.3, 30%, divided by 1 minus 300, divided by 1000, the temperature of the hot reservoir, and this is 43%. So even though they have the same efficiency, the same thermodynamic efficiency or first law efficiency, it seems that machine B could be performing better. Okay, machine A performs better than machine B as far as the second law is regarded. Okay, so comparing both and summarizing the results, they both have 30% as thermodynamic efficiency, but the second law efficiency of the machine on the left is higher, 60%, than the machine on the right, which is 43%. Okay? The conclusion is that machine A converts 60% of its work potential to useful work. Okay? And machine B converts only 43% of its work potential to useful work. Okay? So another possible definition, and more, I would say even more useful for other applications than simply comparing two machines, is this one. The definition of a second law efficiency is useful work divided by the actual useful work divided by reversible work, or exergy. Okay? If you think in terms of exergy, that's the exergy that you actually recovered here in this green arrow, divided by the exergy content in this heat flow here, okay? In the heat supplied to the machine, the heat that is driving the machine, okay? Supplied exergy. And since what we do not recover is what we destroy, we can rewrite this expression as 1 minus destroyed exergy divided by supplied exergy. So if our machine is reversible, we're not destroying exergy, so this is 0, and our second law efficiency is 100% because our machine is reversible. So bottom line is that the second law efficiency is a measure of, let's say, the distance between our actual machine and a reversible machine, which has the maximum first law efficiency. Okay, so that's a very useful way of interpreting this definition here. Okay, so let's analyze this in terms of how exergy, because we just obtained a definition of exergy for open systems, and we also obtain a definition for what we're calling second law efficiency. So let's see how exergy can be transferred to and from a system. Okay, this is going to happen through heat, work, and mass flow, and we're going to analyze individually each one. Okay, so just to remember, thermodynamic heat, exergy of a closed system, and possible other components: mechanical exergy, chemical exergy, magnetic exergy, and so on and so forth. Okay, so the first important observation here is that exergy is a thermodynamic property. That means that it is a state property. I used to say that thermodynamic properties are like GPS coordinates that you use to define a point on Earth, okay? And so this pair of properties are used to define a thermodynamic state. So you always need two properties, the canonical ones, pressure and temperatures, okay? But you can also define a state in terms of its entropy and exergy, okay? So if I give you, well, let's see this. I'm going to allow myself to interrupt the presentation. Let's go to RefProp. Let me show you where you can get these properties in this type of software. Okay. So it's okay. Continue. First, let me show you where you find exergy. Okay. So you go to properties here, because by default it does not show you exergy. I think it's special property, flow exergy. So I'm just checking here to make sure that it's going to calculate exergy. Okay. So as I was saying, and the fluid here is water. Let's change it to air, pseudo-fluid mixtures, air. Okay. And let's calculate a specified state point. So I said that exergy is a thermodynamic property. Okay, so we know that a pair of thermodynamic properties define a state. That means that you can calculate many other properties, okay, just by giving two, like GPS coordinates on a map. Okay, let me just show you some more properties. Options, units, no, not this. Options, properties. Let's calculate, for instance, internal energy, Gibbs free energy, and okay, and let's say viscosity. Okay, thermal conductivity. Okay, that's okay. Okay, just to have lots. So specified points. If I give you temperature and pressure and press enter, it calculates all other properties: density, volume, specific volume, and so on, Gibbs free energy, and flow exergy, as I just calculated. You can ask yourself, well, where's the definition of the environment? Well, you can define in options, properties, reference state here, okay, reference state, and Exergy reference state. So I'm defining the flow here is 25 degrees Celsius, and well, it took 0.01 bar. Okay, I could be using 1 bar, and the amount of Exergy is going to be different. But that's just our definition of environment. Okay, 1 bar, and flow Exergy is 0. Okay, because now the pressure of the system is equal to 1 bar. Okay, but this also means that, as I said here in my presentation, Exergy is also a property, so it can be used to define a state. That means that if you say that the Exergy is 0 and the temperature is 25, okay, if I if I input these two GPS coordinates, when I press enter, it's going to be able, well, not in this case. Perhaps if I use here, let's see. I'm improvising here, so that's why sometimes it does not work. 25, yeah, okay. Let me rephrase, because this is still true, okay? You can use Exergy to define a state, but sometimes, well, in this case, RefProp is not prepared to take Exergy, in this case, as input. You know, let me erase this. I can specify a state by specifying temperature and, for instance, enthalpy, 424.44. When I press enter, now I changed the reference state. So let's start all over again. 25, 1 bar, because I'm not sure of what I've done. So 25, and if I 424.44, okay, I made something strange. Okay, yeah, I know. I'm gonna get this right. So I'm going to specify 25, 1 bar. Okay, so I'm going to define 1 bar, not temperature. And I'm going to explain in a while what I'm doing wrong. 44. Okay. Now I'm able to calculate. Did you see what I just did? I defined a temperature and pressure. In the second line, I defined pressure and enthalpy, and it calculates other properties. Okay, I can do the same. Theoretically, I can do the same with Exergy in any other pair of thermodynamic properties, but I can have numerical problems. Why is this? Let me explain here. Why is this? For instance, I'm saying that, let me draw something here. suppose that I have the relation between, let's say, pressure and temperature. Okay, so if this relation is something like this, let me use a different color here. If this relation is something like this, okay, so it's very easy to input pressure, okay, and you calculate temperature, okay, and also in the opposite sense, I can input temperature and calculate pressure, okay, no problem. But if, let me make another graph here. If this is not the case, if the relation between temperature and pressure is something like this, okay, if I input pressure, okay, no problem, I'm going to calculate the corresponding temperature, but in the opposite sense, it's very numerically difficult. Why? Because, well, a small amount of error, numerical error or imprecision, will mean that well, my pressure may be varying between this very large interval. Okay, so you may have numerical problems in calculating in some particular senses. Okay, that's what just happened here in RefProp. I was trying to use a variable where it's theoretically possible to calculate, but I would have to have infinite precision. Okay, so that's just what happened. Well, I try to improvise here to justify that Exergy is a thermodynamic property or a state property, and well, it seemed that the opposite is true. It's not a thermodynamic, but it's actually a numerical problem. Okay. Well, let's move on. Okay. So let's see. As I was saying, okay, I'm going to analyze how Exergy can be transferred to and from a system. So let's first analyze Exergy transfer through heat. Okay. Let's see what happens when we have heat transfer through a brick wall. Inside this place here where I am right now, it may be, let's say, 25 degrees, and outside today here in São Carlos, possibly 32 degrees. Okay, so there's heat flowing from the environment outside to the atmosphere inside this room, okay, because of this temperature difference. You know, what maintains the temperature at 25 is the AC, air conditioner, okay? It maintains the difference. Well, if we plot the temperature as it's shown here, from outside to inside, we have a higher temperature outside, okay, here, and it starts to drop through the brick walls, okay, and then we have 25 degrees inside, okay. So we have this, and we have this, this heat flow. How can I measure the Exergy content of this heat flow? Okay, follow me. To do this, I have to use my Exergy meter. Remember? Our Exergy meter. And this Exergy meter is actually a Carnot cycle, a Carnot thermal machine, working between our heat source and the environment. Okay, so I'm going to do this. Okay, I'm plugging my Exergy meter between the heat source, which is Q, here, and the environment, which is at the temperature here is T0, okay? The environment, the reference environment is at T0, okay? So the Exergy content on the left side is x, okay? X, let's say x, x, I don't know, x left, okay? So I calculate this, it's the flux Q multiplied by Carnot's efficiency, the efficiency of the Carnot machine, okay? Which calculates 1 minus T0 over TQ. TQ is this temperature here, okay? And the same on the other side of the wall. This, let's say, left, right, x. Okay, so it's Q multiplied by the efficiency of this thermal machine, which is 1 minus T0 over TF. TF is the temperature inside the room. So you see, since we know that TQ is greater than TF, it's obvious that X on the left side is greater than X, the Exergy content on the right side. Okay? You can ask yourself, well, but it's the same amount of heat. How can the same amount of heat contain different Exergy contents? Can carry different contents of Exergy? Okay? The answer is because the temperature is different. Here is TF and here is TQ. Okay? And that's the same question I asked you. What do you prefer in order to generate energy? 1,000 tons of water at 90 degrees or 1,000 tons of water at 25 degrees? From which 1,000 tons of water can you generate the greater amount of energy? Well, it's going to depend on the temperature of the environment. If the environment is at 25 degrees, it's obvious you obtain more energy from water at 90 degrees. But if the environment is at, let's say, 80 degrees, water at 25 can generate more energy. Okay? So it depends. So that's what Exergy is accounting for. The difference in the relative environment. The environment on the left, or the temperature of the heat source on the left and on the right, relative to the temperature of the environment. Okay? So if we draw a Sankey diagram, we see that, well, there's Exergy flowing from the outside to inside the room, and some amount of Exergy is being destroyed, okay, due to this finite difference in temperature here, okay. So this is Exergy being destroyed due to irreversibilities, which is one or two or three phenomena from a list of phenomena that generate entropy. So delta T less than infinite, finite delta T, chemical reaction, mixture, shock waves, supersonic shock waves, and so on. Okay, friction, very important one, friction. So those are irreversibilities that generate entropy that causes Exergy destruction. Okay, we can also make so actually Exergy is analogous to entropy, but the entropy is not energy. Okay, the unit of entropy is watt per or joule per Kelvin, for instance. Sorry, and the physical unit of Exergy is joule, the same as joule. Okay. But the same analysis could be done in terms of entropy analysis, okay? So the amount of entropy flowing into the room is Q divided by TQ. So Q is the same here and here. Let me erase. So the amount of heat is the same here and here, but the temperature is different, okay? TQ is greater than TF, so the entropy content here is higher, or the entropy is higher than here, okay, greater than here. And this is because of entropy generation, actually because delta T is finite, okay? Okay, so, well, we had already seen how to calculate exergy from heat flow, okay? Yeah, and if you want to calculate the exergy content at these specific points, or the overall exergy destruction, you simply integrate this, okay? Just in the same in terms of entropy, okay? So another possibility of transferring exergy is through work. Let's see it. It's actually easier. Just to remember the definition for our closed system, we have our orange substance, okay? It's expanding, or it's going into equilibrium with the environment, so it's going to produce some useful work, and also some amount of work which is spent on the environment. So the amount of exergy is actually exergy associated with work at the boundary, because that's force times displacement, okay? Subtracting the amount of work that is being spent in order to compress the atmosphere, okay? So that's for the closed system. For the open system, okay, yeah, so just an observation. This we know how to calculate. That's PdV, that's force times displacement, and this is P0 delta V. We have seen this, okay? And for the open system, it's a lot easier because, well, let me ask you a question. That's the orange substance in the closed system. In our open system, let's assume that it's this centrifugal pump here, okay? My control volume is this red surface here, okay? We have mass entering here, mass going out here, okay? And I have mechanical work being applied, being injected through this axis here, okay? Let me ask you a question. Is there variation? Is there a surface that is moving, a surface belonging to the control volume that is moving and applying force on the environment? In the case of the open system, okay? No, the surface of the pump is not deforming. You only have mass entering and mass exiting, but there is no boundary work. We also call this component here boundary work, because there is no displacement of the boundary. The boundary was here, the boundary of the control volume was here, and then now it's here. So it deformed, it experienced displacement. And in this case, no. At least in this example, no. There is no deformation of the boundary of the control volume. So the amount of exergy is exactly the amount of work injected in the control volume, okay? And if I do the same analysis, not on the pump, but on this electric motor, I arrive to the same conclusion, okay? So for the open system, I don't have to take into account the work. Usually I don't have the work spent to compress or expand the atmosphere, the environment, because usually our surfaces are not deforming, okay, as is the case in this example, in these two examples, the hydraulic pump and the electric motor, okay? So it's very simple. Let's see now how we can transfer exergy through mass flow, okay? Okay, so as I was saying, mass contain exergy. I just showed you in ref prop here, okay? Well, not for this state here, but let's see, 200 degrees, 20 bar. Okay, I have a certain amount of exergy here. Okay, certain amount of exergy here. Okay, so mass contains exergy. It also contains energy, entropy, Gibbs free energy, and so on. Okay, and our definition of exergy, or of the mass carried, the exergy content of mass, we have this definition, this working definition. Okay, our system is also absorbing heat, positive or negative. Okay, this is the positive sense, and it is also exporting work, positive or negative. Negative work means that it's actually absorbing work, as it is the pump here. Okay, work here is negative. Okay, so it's very, the amount of mass or the amount of energy associated with heat we have already seen. We plug our exergy meter, okay, to measure that. Okay, remember, this is equal to 1 minus T0 minus, let's say, T source, okay, multiplied by Q. Okay, we have seen this. This is actually equal to work, because virtually the surface here is not deforming, it's not compressing the atmosphere, so work equals W. We're going to consider this in a few moments, okay? And the exergy associated with mass flow, simple. You multiply the specific exergy by mass flow, okay? So just like enthalpy, just like entropy, and so on. So it's very, very, very simple, okay? Now let's try to make something that we did for the first law of thermodynamics. I mean, we did energy accounting. Let's do exergy accounting, okay? So when we try to account for all components of exergy, let's see here, okay? We have exergy associated with heat entering the control volume, okay? We have exergy associated with work being exported, okay? We have exergy entering associated with mass flow, okay? And we have exergy, mass flow input, and we also have exergy associated with output flow, okay? We have destruction of exergy, so I'm subtracting, okay? And the sum is equal to the variation of my exergy balance, okay? In my, let's say, check account, exergy check account, okay? So let's try to write down all these components, because we already know how to calculate this, okay? So it's this. This expression here is very important, because we're going to apply this to the problems next weeks, okay? So this term here, well, I'm using a sum because there may be several heat flows at different temperatures, okay? So the exergy content of these heat flows, they all calculate like this. It's the heat flow multiplied by the Carnot efficiency, okay? And here you have the temperature associated with this heat flow, with this, if it's a substance, a heat-carrying substance, okay? Well, here you have input mass flows, exergy associated with input mass flows, exergy associated with output mass flows, exergy destruction, variation of the exergy contained inside the control volume, and this term here, I'm dividing in two parts, okay? W is the exergy content associated to the surplus work, And this term here actually is exergy being exported due to deformation of the control volume. Okay? If this surface here is deforming, and if it's compressing the atmosphere, okay, so pressure is P, the force is P, and the displacement is dV dt, okay? In 99.99% of the cases, this term here is zero, okay? Because, well, actually, this surface is here, or, well, it can be zero because of two reasons. Because we are in permanent regime, our system is not varying in time, but also because this surface is rigid, it's not deforming, okay? So this expression, we're going to use it a lot on next class because it's very, very, very useful, a very interesting analysis tool, okay? I'm not going to have time to show you the example. Now, this is an example. I'm not going to have time, but it's already on video, okay? I'm going to send you the link. But this is an example of an energetic analysis of a combined thermal power plant. And actually, it's a tutorial class. By coincidence, I taught this class yesterday, okay? I'm making an energetic analysis on this system, a regenerative boiler plus a turbine, okay? So it's already on video. You can look at this address in Portuguese. This is not yesterday's video. Yesterday's video, I think it's already posted on my channel on YouTube, but this was done last year, okay? Well, anyway, you have the link here, okay? And it's a tutorial class. This means that in addition to describing all the equations, I also construct all the calculations, the spreadsheets, in order to make this exergetic analysis, okay? Another thing that we're going to see next week is, well, because as I was saying, this is, to now, I already completed all the fundamental concepts associated with Exergy. Now I want to show you two things, two applications, two and a half applications of energetic analysis. Energetic analysis actually corresponds to apply this expression here in some kind of system, okay? I'm going to elaborate two applications. The first one is separation. It's a very, very, very important, one of the most important process in industry is separation. When you produce separation and transformation, okay, the two most important process, okay. So we're going to apply this equation, which implements exergetic analysis, to a system that is separating. For instance, I have a mixture of A and B. Oh, sorry, A and B, and this separates A and B here. Okay. Question: is it necessary to spend electricity, exergy, to make this separation possible? If the answer is yes, and the answer being yes, what is the minimum amount of work that I must spend in order to obtain a perfect separation like this? Okay, so this is a very, very fundamental application in industry. When you produce ethanol, for instance, it's mixed with water. You have to separate ethanol from water in order to make a proper energy vector, which is ethanol suitable for internal combustion engines. So you have to increase its concentration. what's the minimum amount of exergy that you expend, okay? Spent. The other application is more related to the environment. So I'm going to show you this on next week, actually. And I'm going to talk about chemical exergy. Next week, I'm going to talk about chemical exergy, and we're going to make a calculation, an interesting calculation. Suppose, I remember I told you in my first class about what I call a sun-powered or sun-driven CCS industrial plant. I mean, an industrial plant that produces chemical compounds and energy in order to sustain our lifestyle, but it also captures and stores CO2 in the underground as supercritical CO2, remember, and it takes energy from the sun. So, how much energy is it necessary to reconstitute Earth's atmosphere to its original constitution? Okay, the problem is like this. I want to do something in order to avoid the atmosphere heating, increasing of the greenhouse effect. To do this, I have to remove CO2 from the atmosphere. It's a separation process, okay? Removing CO2 from the atmosphere is a separation process, okay? So, if I want to, today the concentration of CO2 is around 400 ppm. It's not yet at 400 ppm. And concentration of CO2 in the 1800s was around 300 ppm. Okay, just nice round numbers like this. If I want to remove CO2 from the atmosphere in order to obtain the CO2's concentration before the Industrial Revolution, how much energy did I have to spend? I mean, is this impossible? Is it feasible or is it impossible? We're going to do this calculation by applying these concepts here, okay? So this is what we're going to see next week, because I'm going to be talking about next week and the following week, because I'm going to be talking about chemical exergy and exegetic analysis and some example processes, okay? This is one. I'm going to show you, well, this is already in video, so I'm going to show you a more detailed problem. Actually, this problem here, the CCS power plant. Okay, we're going to make a complete exegetic analysis, and also I think I'm not sure. I'm going to talk about internal combustion engines. Make exegetic analysis to internal combustion engines. Okay, so I think this is it. Actually, I was fast today. You didn't answer any questions, so I just move along. Okay, do anybody have some question? Okay, so that's it.
Professor.
Yeah, go on.
Professor, I have a question, but I think it's easier if I talk in Portuguese.
Okay, yeah, please go. I can Yeah, you can. I can translate to English if someone wants to. Okay, go on.
And that's because I don't know a lot of words I will say. So.
Okay.
A questão que eu tenho é a seguinte. Se a gente trabalha, por exemplo, tem um monte de sonda espacial para gerar eletricidade, usa o efeito termopar.
Sim.
Você tem uma fonte quente de plutônio e a fonte fria é o espaço.
Uhum.
Esse seria, acho que, o exemplo mais fácil para trabalhar com energia, porque ali só tem que considerar a diferença de temperatura entre os dois meios para gerar uma potência. Aí eu dei uma procurada aqui no Google e não encontrei nada sobre isso.
Let me just translate. He's asking about the thermocouple effect, okay? And how can we apply exegetic analysis to this system in space for space applications, like in a satellite, for instance. So what you need to generate electricity in space, you need some source of heat, which will heat the hot side of the thermocouple, and the cold side is going to reject heat to space, actually, which is around the temperature. The background temperature of the universe is around 4 Kelvin. Okay, the background temperature of the universe is around 4 Kelvin. So it's a very low temperature, and that means that you can actually generate a lot of electricity. Very frankly speaking, I don't know how to answer your question, because I never saw this kind of application of the exergetic balance equation. Okay, I have to think a little bit. I tend to believe that since you have to reject heat, this system, okay, the thermocouple here, I don't know if you guys are aware, I have, let's say, material A here, some metallic material A here, and a metallic material B here, for instance. B. 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 And here I have, a current meter. Okay. If I have a temperature difference, let's say, it can be 25 degrees Celsius here, and 4 Kelvin here. Okay. So because of this temperature difference, you're going to start having a electric current here. I tend to believe that it's possible to apply all these concepts because you have to have this temperature difference. Okay, so I still, first law and second law always apply. They always apply. Of that I'm sure. But I'm not sure how to apply to this particular system. So I cannot actually answer your question, okay? So this is a limitation of my part, okay?
I will try to find an answer too.
Yeah, if you do, please bring it to us, okay? I'm sure this will be very interesting, okay? And the same goes to all of you. If you have particular applications, that's a very interesting place to discuss. This application is here, especially if it's closely related to the class being taught that day, okay? That's a suggestion that I actually forgot to give you, okay? We're going to talk about solar energy. We have a class on thermal solar energy. I'm going to be talking about radiation, heat radiation, okay, during this class. But the thermocouple effect, I'm not talking in this course, okay? So, sorry, I cannot answer your question, okay?
No problem.
Okay.
Thank you.
Okay, any more questions? Okay, so just give me a moment here. I'm going to show you where to find. Let me go to my channel here. This is the tutorial. The tutorial that I was talking about is here. Okay. Oh, sorry. Here. I just wanted to show what I mean by tutorial class. Okay. Let me cut sound. So I'm. Let me see here. So I'm building a spreadsheet with all calculations from scratch. Okay. I start from a blank spreadsheet, and I make all the calculations, how to call refprop functions within the spreadsheet. So it's a tutorial class on this problem here. Oh, okay, this was yesterday's class, and the problem it's not responding. I don't know what's happening. Okay, anyway, it's related to this system, regenerative boiler in the turbine, exergetic analysis. There is also, let me show you another thing here. How can I show? There is also another thing that I wanted to say is that, let me see. Last year I taught this class in Portuguese, and all classes are already in video. So if you go to my playlists here, okay, if you go to my playlists and if you look for, there are several playlists. This is the exergetic analysis of the CCS thermal power plant. This is our last classes, but there's a list called renewable energies and energy planning. So here in this list you have 18 videos with all last year's classes, okay, which are in Portuguese. It's yeah, almost the same. Okay, so if you have doubts, you can, or if you lose one of our class, you can watch this last year's videos. Okay, that's something that I wanted to say. Another important, very, very, very important thing that I want to say to you is that, where is it? There's also a list. It's still in Portuguese, but this is easier to find in English from other universities. There's a complete course on thermodynamics. Where is it? My list? Yeah. No. Yeah, here. In Portuguese, Curso de Termodinâmica. So I teach this course for the undergraduate students. It's completely in videos. And for instance, today I talked about, today I mentioned a lot about entropy. So there are three videos talking about entropy if you want to get deeper into this subject. Okay, so if you want to have a better understanding of all the fundamental ideas, I highly recommend you to watch some of these videos. Okay, so I have here entropy. The definition. Today's class is actually this class, okay? Introduction to Exergy, and we have well, tutorial class and so on, okay? So that was some warnings that I wanted to pass you guys, okay? Okay, so if there's no doubt, we're a little bit earlier today. Okay, thank you very much for watching.
Thank you. Thank you, teacher. I appreciate it.
Okay, thank you.